Let's look at the sun, without ruining our eyes, of course. We'll use a filter that cuts out 99.999% of the light. What we see is a luminous, nearly featureless, limb-darkened disk. It doesn't give us many clues about what the sun is. Images at other wavelengths that emphasize the high-energy phenomena can be much more dramatic. We can see glowing, hot material welling up through what look like cracks in the photosphere. Flares blast away from the surface like a sorcerer flinging fireballs. While we're admiring these images, let's ponder a number. 3.8 times 10 to the 26. That's the sun's luminosity in watts. In this lecture, we're going to perform some calculations to try and understand that number. You might want to get out your calculator so you can follow along. 3.8 times 10 to the 26 watts is a clue about what's happening inside the sun. It is a lot of power. The Earth intercepts less than a billionth of the sun's total luminosity, and yet even that tiny fraction amounts to 10,000 times more power than all the world's power plants put together. And what's more, the sun has been shining a long time, 4.6 billion years, based on evidence from primitive meteorites. Geologists have found evidence that liquid water oceans have also existed for billions of years, so the sun's luminosity couldn't have been much lower in the past, or else those oceans would have frozen. With these numbers, we can calculate the sun's total energy output since it formed. We multiply the sun's luminosity by its age, giving 5.5 times 10 to the 43 joules of energy. Where did all of that energy come from? Maybe the sun is burning a fuel, the way a lantern burns kerosene. Let's see, how much kerosene would be required? The combustion of 1 kilogram of kerosene releases 46 million joules, megajoules, of heat. The required mass of kerosene is therefore 5.5 times 10 to the 43 joules divided by 46 megajoules per kilogram. That gives 1.2 times 10 to the 36 kilograms. But today, the sun's mass is only 2 times 10 to the 30 kilograms. So it's 500,000 times too small. Even if the sun were made of pure burning kerosene, it could shine for only 9,000 more years. Okay, maybe it's some other chemical fuel with a higher energy output per unit mass. But no, that can't be either. Chemical reactions involve electrons changing orbits or getting traded between nuclei. As we saw in Lecture 2, the energy scale for those transitions is always on the order of 1 electron volt per proton mass. It's the scale that's set by the marriage of electromagnetism and quantum theory, and it's equivalent to about 100 megajoules per kilogram. You'll never find a chemical fuel that's orders of magnitude better than that. So we need something else. Early astrophysicists thought that that something was gravity. The way a star forms is that a tenuous cloud of gas contracts under its own gravity into a smaller, denser ball. But we shouldn't imagine this process as a perfect sphere of gas whose radius is getting smaller. The initial cloud was very patchy and irregular. And so as it collapsed, streams and clumps of gas fell toward the center, crashing into each other, producing radiation and shock waves and a lot of heat. The net effect was to convert gravitational potential energy into heat. To calculate how much heat, we start with the fact that the gravitational potential energy of a uniform sphere, a ball of constant density, is minus 3/5 gm squared over r, where m is the mass and r is the radius. The gm squared over r you could have guessed from dimensional analysis. It's the only way to combine g, m, and r and get the units of energy. And the 3/5 comes from doing the problem exactly, with calculus. Now, the sun is not a ball of uniform density. It's denser on the inside than the outside. But we'll neglect that for this order of magnitude calculation. And that initial cloud was so much larger and more diffuse than the sun that its energy was essentially zero by comparison. So the energy released as heat was 3/5 gm²/r. And when you plug in the numbers for the sun, that comes out to 2.3 times 10 to the 41 joules. That's still too small, by a factor of 240. If gravity had been the only power source, the sun could only have sustained its luminosity for 20 million years, not 4.6 billion. What we just did is a famous calculation in the history of science. In 1862, Lord Kelvin used the same logic to argue that the sun, and by extension the Earth, couldn't be much older than 20 million years. That led him and others to doubt Darwin's new theory of evolution by natural selection. Darwin needed too much time for creatures to evolve. What Kelvin didn't know was that within a few decades, his colleagues would start exploring the atomic nucleus. As you probably already know, the answer to the riddle of the sun's energy is nuclear fusion. Nuclear reactions involve rearrangements not of the electrons, but of nucleons, protons and neutrons. The typical energies involved with those rearrangements are millions of electron volts. That's the factor of a million that we need beyond what chemistry can deliver. That's what gives the sun its longevity, and what gave evolution enough time to go from bacteria to Bactrian camels. And that's why we're going to need a crash course in nuclear physics. First, let's remember that an atomic nucleus is a tiny bundle of protons and neutrons at the center of a cloud of electrons. In a neutral atom, the number of protons equals the number of electrons, since they have equal and opposite electric charges. The number of neutrons is always about the same as the number of protons or somewhat higher, for reasons we'll discuss shortly. For example, a carbon atom has 6 electrons around a nucleus of 6 protons and 6 neutrons. Some carbon nuclei, though, have 7 neutrons. We say carbon has 2 main isotopes, nuclei with the same number of protons, but different numbers of neutrons. You might wonder, why do we call them both carbon if their nuclei are different? Why don't we just give each nucleus a different name? It's because elements are named by chemists, not nuclear physicists. The chemical properties of an atom depend almost entirely on the number of electrons, which is equal to the number of protons. The neutron count doesn't matter so much. But it matters a lot for nuclear reactions. When carbon is involved in a nuclear reaction, we need to know which isotope we're talking about. The convention is to specify the total number of nucleons, protons plus neutrons, which is often called the atomic mass and represented by the letter A. For example, carbon-12 has 6 protons and 6 neutrons, so A equals 12. And we write it as a C with a 12 in the upper left. Another big difference between chemical and nuclear reactions is the spatial scale over which the changes occur. Remember, if we expand a carbon atom to the size of a football field, most of that space will be filled by the electron cloud. The nucleus would be less than a centimeter across. The smaller scale of nuclei and the million-fold more energy that's released are both consequences of the strength of the strong nuclear force and the short range over which it acts compared to electromagnetism. Let's be more quantitative. In chemistry, a key concept is the heat of formation, the amount of energy released if you make a molecule from its elemental constituents. For example, if you mix hydrogen and oxygen to make water, you release 2.5 electron volts per water molecule. That's the heat of formation of water. Well, the analogous concept in nuclear physics is the nuclear binding energy. It's defined as the energy released if you make a nucleus out of free protons and neutrons. Or equivalently, it's the energy required to completely disintegrate a nucleus. Carbon-12, for example, has a binding energy of 92 million electron volts, or MeV. Now, it would be impossible to slam together 6 protons and 6 neutrons all at once to make carbon. In reality, you would have to perform a sequence of simpler steps involving only 2 nuclei at a time. But it doesn't matter. The difference in binding energy between the starting and ending nuclei doesn't depend on the path you take to get from one to the other. The binding energies of all the most stable isotopes have been measured in laboratory experiments. Let's look at a chart of the measured binding energy, B, versus the atomic mass, A. The x-axis ranges from hydrogen at A equals 1 to uranium at 238. The data form an upward-sloping, nearly straight line. That makes sense. The bigger the nucleus, the harder we need to work to tear it apart. The slope, B over A, tells us how hard. Based on the chart, it's about 2,000 MeV divided by 250, or 8 MeV per nucleon. But despite appearances, the line isn't exactly straight. Let's get a clearer view. Instead of plotting B, we'll plot B over A versus A. Now we see it's not as simple as 8 MeV per nucleon. Small nuclei have a relatively low binding energy per nucleon. B over A then rises to a maximum value at an atomic mass of around 60. The winner is nickel 62, followed closely by iron 58 and iron 56. Those are the most stable nuclei. If you had a bunch of protons and neutrons, and you gave them the opportunity to mix and match however they want, they would tend to clump together into nickel and iron. That's how they achieve the lowest possible energy. Which might make you wonder, why isn't everything made of nickel and iron? The answer is, nature doesn't provide nucleons with the opportunity to mix and match however they want. Nuclear reactions require high densities and temperatures because nuclei are all positively charged, so they repel each other. But when conditions do allow for spontaneous nuclear reactions, they will tend to produce nuclei that approach nickel and iron. Smaller nuclei will tend to merge together. That's fusion. Larger nuclei are vulnerable to breaking apart, which we call decay if only a little piece of the nucleus breaks off, or fission if it breaks into chunks of comparable size. In this sense, the light nuclei, like hydrogen, helium, and carbon, want to fuse. And heavier elements, like gold, lead, and uranium, they wish they could break apart and become more like nickel and iron. Let's try to understand why the binding energy curve has this shape. Think back to our mental model of a nucleus as a cluster of marbles. Each one's coated with glue. That's the strong nuclear force. If a marble is surrounded by other marbles, it takes about 8 MeV of energy to overcome all the glue and to pull it out. That's the average value of B over A. But that's not all there is to it. Some of the marbles are near the surface of the cluster, so they're not surrounded by marbles in all directions, and they're not glued as tightly in place. That lowers the binding energy relative to the average. This surface penalty is especially bad for small nuclei because they have the highest surface-to-volume ratio. The surface area of a sphere grows as radius squared, and the volume goes as radius cubed, so the surface-to-volume ratio varies as 1 over radius. It gets worse for small nuclei. Another problem is that some of those marbles, the protons, repel each other. The electric repulsion works against the glue, lowering the binding energy. So there's a penalty for having protons. Then why would a nucleus want to have any protons? Why don't we see nuclei made entirely from neutrons? It's because of another effect called symmetry energy. Roughly speaking, the glue that sticks nucleons together is a little stronger when it's between a proton and a neutron than it is between two protons or two neutrons. That increases the binding energy of nuclei with lots of proton-neutron pairs. Now we can understand the shape of the binding energy curve. Light nuclei suffer from high surface area. That's why their binding energy is lower than average. Very heavy nuclei also have low binding energies because they suffer from an internal conflict. As you keep adding nucleons to a nucleus, you'd like to avoid the proton penalty and stick with neutrons, but to satisfy the desire for symmetry, you need to add some protons, and the net effect is to destabilize the nucleus. You may have also noticed there are some spikes in the binding energy curve that I haven't explained yet. Let's get a better look at them by zooming in on the lightest nuclei. These enhancements in binding energy come from aspects of the strong force that favor even numbers of protons and even numbers of neutrons. Helium-4, for example, has 2 of each, so it's blessed with an especially high binding energy. Also in this category are beryllium-8, carbon-12, oxygen-16, and neon-20. Now, let's return to the Sun and the problem of explaining its prodigious energy. We know from its spectrum that the Sun is mostly hydrogen. So could it be using hydrogen as a fuel, fusing it into helium? The stable nucleus of hydrogen, H1, is just a proton with a binding energy of 0. Helium-4 has a binding energy of 7 MeV per nucleon. So hydrogen fusion releases 7 MeV per nucleon. That's equivalent to 670 million megajoules per kilogram. That's 15 million times more than you get from burning kerosene. But is it enough to explain the Sun's total energy output? Let's calculate the required mass of hydrogen. It's the Sun's total energy output divided by the energy per kilogram released by fusion, giving 8.2 times 10 to the 28 kilograms, or equivalently 0.04 solar masses. By converting only 4% of its hydrogen into helium, the Sun can release enough energy to shine for billions of years. Speaking of mass, let's take this opportunity to talk about the close relationship between mass and energy, the one Einstein taught us about, E equals mc squared. What this means is that, despite what we teach in freshman physics, energy is not conserved, and neither is mass. Interactions can change one into the other, and the exchange rate is E equals mc squared. Mass and energy turn out to be the same kind of stuff at a fundamental level. It's their combination that's conserved. An important implication is that when an interaction releases energy, whether you're burning kerosene or fusing hydrogen, the total mass of all the particles involved must go down. The change in mass, delta m, is equal to delta E over c squared. This happens during chemical reactions, but we never notice it. The changes in mass are only at the level of parts per billion. But for nuclear reactions, the changes are more substantial. Let's calculate the fractional change in mass, delta m over m, for hydrogen fusion. We'll take the 7 MeV per nucleon that's released during fusion, divide by c squared to get the corresponding mass loss, and then divide by the mass of a proton to make it into a fraction. The number comes out to be 0.0075. So if this is correct, we should find that a helium nucleus is less massive by 0.75% than the sum of 2 isolated protons and 2 isolated neutrons. Which is true. The difference in mass can be measured directly in laboratory experiments. All of this implies that the sun, like anything that radiates energy, is losing mass. We can calculate how much. In time dt, the sun emits an energy, dE, and loses a mass of dE over c squared. So the rate of mass loss is dE dt over c squared, where dE dt is the sun's luminosity. Dividing the sun's luminosity by c squared, we get 4 × 10⁹ kilograms per second. That's right. Every second, 4 billion kilograms of mass are vanishing from the sun, having been converted into energy and flung out into space. But don't be too concerned. The sun is not going to disappear anytime soon. Remember, its total mass is 2 × 10⁻30 kilograms. Even after 10 billion years, the sun will lose only about 0.07% of its mass in this way. Now, let's change gears. To this point in the lecture, we focused on calculating differences in energy or mass before and after some interaction, whether chemical, gravitational, or nuclear. That led to some important insights, but the knowledge of energy differences alone doesn't tell us anything about the mechanisms of the reactions. By what specific steps are the 4 protons converted into helium? That's a much tougher question. In fact, even after it became clear that the sun's luminosity has a nuclear origin, the sequence of reactions was the subject of confusion and debate for decades. We can't expect 4 protons to crash into one another all at the same time. Such 4-body collisions are vanishingly rare. The only plausible reactions are 2-body collisions. So, you would think the first step would be to smash 2 protons together and make helium-2. But there are a couple of problems. The first problem is that protons repel each other. How do we get them to approach each other closely enough for the strong force to take over? We can represent the problem schematically by plotting the potential energy of a proton as a function of its distance from another proton. As we bring the protons together, the electric potential energy rises. It's eta times E squared over R, where eta is the Coulomb constant and E is the proton's charge. But if they manage to get to within 1.5 femtometers, that's 1.5 × 10⁻15 meters, then the strong force can take over and the energy goes way down. The marbles have come close enough to touch and stick. To find the maximum height of the potential energy barrier, we need to evaluate the electric potential energy of 2 protons separated by 1.5 femtometers. That comes out to be 1 MeV. So if we want the protons to stick, we need to throw one at the other with at least 1 MeV of kinetic energy. If it only has 1/4 of an MeV, the repulsion will cause it to slow down, halt at 5.5 femtometers, and then fly away. So the question is, do the protons at the center of the sun have at least 1 MeV of kinetic energy? Well, we have good reason to believe that the temperature at the center of the sun is 15 million degrees Kelvin. It's based on a calculation we'll perform in the next lecture. And we know the average kinetic energy per particle in a gas at temperature T is 3/2 kT. Multiplying 3/2 K by 15 million Kelvin gives 0.002 MeV. Now you see the problem. According to this calculation, the sun is way too cold. The protons should have no chance of coming close enough to stick. So how do they even get started making helium? The answer is amazing. You know what helps the protons? Quantum theory. The The time has come to set aside our mental model of protons as marbles. Like any fundamental particle, protons also have a wave-like nature and are described by a wave function, a cloud of probability extending over a region of space. Unlike classical particles, wave functions do not simply halt when they reach a potential energy barrier. They can leak through. The amplitude of the wave function goes down exponentially as it leaks through, so the portion that gets through the barrier is tiny. Nevertheless, there's a chance for a proton to tunnel through the barrier, even though officially it doesn't have enough energy. This phenomenon is called quantum tunneling, and it's governed by the Schrödinger equation. We're not going to solve the Schrödinger equation, but we will perform an order of magnitude calculation to establish how much energy a proton needs to have a decent chance of tunneling through the barrier. Key concept is the de Broglie wavelength, lambda d, defined as h over p, Planck's constant over momentum. You can think of the de Broglie wavelength as the spatial extent of a particle's cloud of probability. When you observe the particle, it won't necessarily be located where you would expect based on classical physics. But you'll find it within about one de Broglie wavelength of that expected location. What this means is that we don't need the protons to get to within 1.5 femtometers of each other. It's enough that their wave functions overlap to within about 1 de Broglie wavelength. And that turns out to be much easier. It doesn't require as much energy. Let's see how that works. The de Broglie wavelength is h over momentum. But we're not interested in momentum, we're interested in kinetic energy, 1/2 mv squared, which is equal to p squared over 2m, and therefore p equals the square root of 2me. So we can rewrite the de Broglie wavelength as h over root 2me. For the protons to approach within a de Broglie wavelength, the required energy is no longer eta e squared over 1.5 femtometers. It's eta e squared over lambda d. That leads to an equation with energy on both sides, which we can solve for energy, and then plug in the numbers. The answer is 0.0025 MeV. That's 3 orders of magnitude lower than 1 MeV, the required energy for classical particles. And it's the same order of magnitude as the average kinetic energy of protons at the center of the Sun. So it all hangs together. By relying on quantum tunneling, protons can fuse even at the low temperature of 15 million Kelvin. An important aspect of quantum tunneling is the exponential fall-off in the wave function as it penetrates a barrier. Because of that, the probability to tunnel through a barrier depends very sensitively on energy. Small changes in energy lead to large changes in the fusion rate. This fact will be crucial for our understanding of stars. Thermonuclear reaction rates, where the nuclei rely on random kinetic energy to come together and fuse, depend very strongly on temperature. The rate of proton fusion in the Sun varies as temperature to the 4th power, and some other important reactions vary as T to the 8th power or even higher powers. What this means in practice is that each reaction has a sharply defined ignition temperature, below which the power output is negligible, and above which it's substantial. This will have important consequences for stellar structure, as we'll discuss in the next lecture. For now, let's be glad we've made progress in understanding hydrogen fusion. But we can't relax just yet. There's another problem. Helium-2, the nucleus made from 2 protons, is extremely unstable. So after all that work bringing the protons together, the nucleus falls apart, and we're back to square one. This, too, was a historical puzzle with a very subtle solution. In this case, what saves the day is the weak nuclear interaction, the one that can convert protons into neutrons and vice versa. What happens is, the The two protons approach each other, and right when their wave functions merge, there's a slight chance that one of them will change into a neutron, spitting out a positron and a neutrino in the process. Proton and the newborn neutron make a nucleus of hydrogen 2, also known as deuterium, which is stable. However, the interaction that allows this transformation is, well, it's weak. The probability is low. If you follow a single proton bouncing around in the core of the Sun, you have to wait several billion years on average before you'll see it fuse into deuterium. But after that, things start happening faster. Within a few seconds, the deuterium smacks into another proton and sticks, forming helium-3 and emitting a gamma-ray photon. And from there are 3 different paths that lead to helium-4. I'll just explain the simplest one. Given enough time, about 20,000 years, a helium-3 nucleus will find another one and collide, knocking away 2 protons. And what's left is 2 protons and 2 neutrons. That's helium-4, the endpoint, which is very stable and interacts no further. At last, we've achieved what we wanted. We identified the Sun's energy source, thermonuclear fusion of hydrogen into helium. And we learned the steps required to fuse hydrogen into helium. Let's close this lecture with one last calculation regarding the Sun's energy. We began by marveling at the Sun's luminosity, 3.8 times 10 to the 26 watts. Now I'd like to ask, what's the average power output per cubic meter in the core of the Sun? The core, where the nuclear reactions are taking place, has a radius of about 70,000 kilometers, about a tenth of the Sun's total radius. So let's take the Sun's luminosity and divide by the volume of the core. The answer in watts per cubic meter is 300. Does that surprise you? 300 watts is not super impressive. My kitchen toaster emits 1,000 watts of heat. What we've just learned is that we should not envision the Sun as a blast furnace with nuclear bombs going off all the time. Far from it. It's much more like a collection of toasters, spaced apart every few meters. What makes the Sun so luminous is that it's so big. There are a lot of toasters. And just as important, the overlying material, the outer 90% of the Sun, is optically thick, so it traps the energy for a long time, keeping the interior toasty hot. I just love thinking about the wide range of physical processes going on inside the Sun. There's gravity to compress the interior, electromagnetism and the strong force setting the energies of nuclear reactions, the reliance of protons on quantum tunneling and the weak nuclear interaction to come together and undergo reactions on timescales ranging from seconds to billions of years. It all seems so utterly improbable. And yet, it's all these processes working together that provide the energy for life here on Earth.